Next up on our probability journey is the interpretation of variables, furthermore, as random variables. We already have the interpretation of variables being quantitative, categorical, explanatory, response. Here's another layer. We can also consider them as random variables. What we mean by that is that the outcome or the value of a variable depends on chance. Therefore, there can be probabilities associated with the possible values of the random variable. Let's touch base a little bit with some notation. Usually, a random variable is represented with a capital letter. Probably the most common are the capital letter Y, because Y makes sense as a response variable, or maybe X. And in defining a variable, this is a description of what is being measured or counted. So you might say Y or X is the height of a tree. So capitalization there. However, observations from that variable are usually represented with lowercase letters. So I might say lowercase y equals 6.1 meters. It's a minor distinction, lowercase, uppercase, but it does make shorthand notation a little easier. We're going to today discuss discrete random variables today, but this can also be expanded to continuous random variables, which is going to be most of the focus in our course, so I'm just going to say later there. Let's pop into an example to illustrate random variables and some properties therein, especially for discrete random variables. In this example, we're going back to coins, and let's consider a fair or unbiased coin being flipped 3 times. I'm going to let a letter represent the number of times a tail was flipped, and I'll use Y to be consistent and sort of general. So the capital letter Y here, it's a brief sentence describing what your variable is, what is being counted. Let's consider the possible values of this variable, lowercase y. If a coin is being flipped 3 times, it is possible to get 0 tails. It is also possible to get 1 tail, or 2 tails, and lastly, 3 tails. And I want to dive a little bit more into these possible values, because I think it's kind of fun to think about. We could draw a probability tree, however, I'm going to spare us the time in doing so. We did that in a previous video. I'm going to give myself a little more space here. Let's consider what 0 tails would look like. Well, wouldn't that be heads, heads, heads? For sure. Let's see what 1 tail could look like. 1 tail in 3 flips. You could have the tail in the first flip. You could have the tail in the second flip. Or that 1 tail could occur in the third flip. So notice there are 3 ways to obtain 1 tail. Let's go to 2 tails. two tails, that can be heads, tails, tails. I'm basically going to do the flip of what we got here. Two tails, which is one head. That one head could be on the first flip, on the second, or on the third. So we've got HTT, THT. That is what we call a heads sandwich on tails bread. And then TTH. So notice, again, there are three ways for two tails to occur. However, there is only one way to achieve three tails, T, T, T. I have hopefully hinted at what is considered a combination, right? There are three ways to get one tail, and there's also three ways here. Where did that come from? Consider 3, choose 2. 3, choose 1. And there's only one way for 3 tails out of a group of 3. Similarly over here, 3, choose 0. So hopefully that kind of connects the concept of combinations, which was from chapter 1, into some of this business here. I think it's kind of fun. Backtrack a little bit. Notice there are 3, 6, 7, 8. There's really 8 possible outcomes when you flip a coin 3 times. Let's discuss the probability of those 8 outcomes. We can discuss the probability that capital Y equals 0, the probability that capital Y equals 1, probability that capital Y equals 2, and 3. Let's take it from this top one here. Since we are dealing with a fair coin, each of these 8 outcomes all have the same chance. One of those 8 outcomes resulted in 0 tails, so that is 1 out of 8. 1 tail, there was 3 out of the 8. 2 tails, also 3 out of 8. And 3 tails, 1/8. What we have just defined here is called a probability mass function, or PMF, probability mass function. And this applies to discrete variables, discrete random variables. We're counting number of tails, right? Discrete whole numbers. And here we've kind of got like a just a list of probabilities. We could even draw this in a type of graph. I've copied a set of axes here and basically going to transcribe these probabilities onto the vertical axis. So I'll label that probability. And our horizontal axis, I can just use the letter capital Y since I have defined it. But if you want to be more specific, you could also just not be as lazy as me and just write number of tails. And I'll put some tick marks here for 0, 1, 2, 3 tails. And I know I didn't put the 0 on the origin here. I just want it to be visible, so I've just offset it. Not a big deal. Our probabilities, going to need a tick mark for 1/8 and 3/8. I'll scale those, so 1/8, 2/8. I won't use you, I know you're a quarter. 3/8. In the past, we drew bars here, but there's another way that we can draw this in the way that R usually does it. So I want to replicate the way R does it. Is because these are discrete values, they're not ranging from -1/2 to +1/2. They're discrete. So sometimes you'll just put a line on those discrete values. So I'm putting a vertical line that's extending up to 3/8 there, 3/8 for 2 tails, and 1/8 for 3 tails. So these are both examples of probability mass functions. Over here in the top, it's a list of the probabilities in written form. Down here, we've got a little graph. Everyone loves a graph. We can even discuss the shape of these probabilities over the number of tails, the shape of this probability mass function. It looks symmetric, right? You might even call that bell-shaped. And do you recall where the mean of a bell-shaped symmetric distribution occurs? Right in the center, yeah? So if we were to determine an average number of tails, wouldn't it be right here at 1.5? Definitely. And how would we compute that? Let's see. That's next. We're going to talk about the expected value, aka the mean of a discrete random variable. The way that this is formulated, we'll call this the mean. And because it applies to a random variable, often they'll put that letter for the random variable down there. So mu capital Y. And this is still a mean, so there needs to be addition and there needs to be division. And what would need to be added are the values for the number of tails. Add the number of tails values. So those would be the 0s, the 1s, the 2s, the 3s. However, those values occur at different rates or probabilities. So we would multiply by the probability of observing those y values. So all this text here is just to say those 1/8 and those 3/8. And we might as well just crunch this right on out for this example. Let's roll. The mean of our random variable, there's going to be a bunch of addition, only four quantities added. We'll start with the 0 tails, and that's going to multiply the probability for 0 tails, which is 1/8. That's going to simplify down to a 0, but I want to write it for thoroughness sake. We're going to add 1 tail times its probability of 3/8. Add it up. 2 tails, you also have a 3/8 probability. Last, not least, 3 tails, probability 1/8. And you certainly could just go and crunch away on your calculator on this, but I'm going to resist the temptation and notice that I've got a common denominator here of an 8. So I can do a lot of work without relying on a calculator. Here, remember that this is like 2 over 1, numerator times numerator, denominator times denominator, 6/8, and another 3/8. So this gives us a total of how many 8s? Looks like 12 8s. Do you see it? 12 8s is another way of saying 1 1/2. So we did it. Our hard work corresponded with our intuition up here. So this would be the expected number of tails in 3 coin flips. So if you were to flip a coin 3 times, and then 3 times again, and 3 times again, and every single time that you flipped a coin 3 times, we know that you might get 0 or 1 or 2 or 3, but on average, they should average to 1 1/2 tails. Something that I think is kind of fun here, let's keep track of this 12 over 8. 12 over 8. I'm going to scroll up. 12 over 8. Let's remember up here, we had those 8 possible outcomes. And could you count up how many letter T's you see here? I'm counting them up. Isn't that 12 tails out of the 8 outcomes? It's kind of fun, huh? Okay. Well, the mean's best friend is standard deviation. Standard deviation and mean are such good friends. Maybe this is what they look like. This is mu, and this is standard deviation. And they like to hold hands. Yay! They're best friends. Okay, enough of that silliness. Let's talk about the standard deviation of a discrete random variable. It still has the interpretation of being typical distance from the mean. But now we've got this new perspective with probabilities. We add up, take our observations, subtract the mean, standard deviation. We square those deviations. That's the sum of squares. And just like earlier, we know that those values occur with different probability, so we need to multiply by the probability of observing those observations. And you might remember a very classic feature of standard deviation. Our last step is always to square root that entire quantity. Let's illustrate this with our coin flip example. I'm going to need some space. Example. Okay, I will write that big square root. I think that will be sufficient. We're going to need to do some additions. But we'll start with 0 tails. We'll subtract the mean. Square times the probability of 0 tails. Cool. That's what they're all going to look like. We're going to have a subtraction squared multiplied by a probability. We'll have a subtraction squared multiplied by a probability. Okay, 0 heads, got it. 1 head minus the mean squared the probability of one tail, I apologize, it's 3/8. 2 tails subtract the mean. Your probability was 3/8. And lastly, we had 3 tails. Subtract the mean. Square. Your probability was 1/8. I would like to have more fun without any calculators present. No calculators allowed for the next couple minutes. I know that 1.5 is the same as 3/2. And you might be asking, why on earth would I think about a fraction? Isn't decimals easier? Not really, especially when you start squaring. For instance, what is 1.5 squared? Do you know off the top of your head? Probably not. I don't. But I know what 3/2 squared is. That is 9/4. It's pretty nice. So that makes our work a little easier, is considering some of these values in terms of fractions. Another value that we're going to see a lot is 1/2, and that will also be squared. We know that's 1/4. Okay, so I had some side action here. Let's get back to the task at hand. Here I see a negative 1/2 squared. I know that those negatives will cancel out when they're squared. So 1.5 squared, that would be 9/4. And I'll just keep that multiplication by 1/8 for right now. Let's see here, 1 minus 1.5. That's negative 1/2. But that needs to be squared, so that would be 1/4. These will all be positive because of that squaring feature, but now we won't have to deal with any negatives. This will be 1/2 squared, which is 1/4, multiplied by 3/8. And lastly, 1.5 squared times 1/8. Another cool thing we've got going here is a common denominator. You might notice that the denominator for all of these is 32. And so we can add up, we'll multiply and add up all of these numerators. Thank goodness these all have multiplications by 1. So we've got 9 plus 3 plus 3 plus 9. That's 24 in the numerator. 24 32nds. Another way to think about that in reduced terms is 3/4. Something that's kind of cool here, for those of you who've taken trig or geometry recently, isn't that √3/2, which is a very popular quantity in trigonometry. And there we go. That is our solution. So that's going to conclude our discussion here on discrete random variables and how we describe their probabilities with probability mass functions. Let's cruise on over to discuss continuous random variables. And we touched on this in a previous video, but we will expand upon that now, in which variables that are continuous, when we draw that smooth curve to represent the probability distribution for the population, we would call that a density function, a probability density function. And I'll draw a bell-shaped or normal curve here, and the axis labels, we often just completely ignore this vertical one. It's kind of a bad habit, but it seems to be discipline-wide. Density, vertical, and we would have our variable labeled here. And we mentioned that we are using area to determine probability, which is why that vertical axis is now density. Therefore, the total area under that curve must be 1. Furthermore, if we want to describe some probability over an interval of values, say between A and B here, we would want to find this, I'll do it in pink. We would want to find that pink area. But let's discuss that a little bit more. I want to talk some notation with you. This pink region, I could denote this as the probability that our variable y is between A and B. And that would be that pink shaded area. I don't know what number that would be. I'll just say that pink zone. Okay. Furthermore, if we wanted to do some other region, we want to find some other probability under this curve related to this variable. Maybe, let's see, green here. We'll do green polka dots. Those green polka dots, how could we represent that with probability notation? Probability that our variable y is less than A. And that's the green zone. I want to ask you a question. Now, there's no numbers, we're not calculating anything here, but I am going to ask you a kind of specific question. Could we find the probability, could we find the probability that our random variable, which is continuous, what is the probability that it equals B? Okay. So area, we need area to obtain probability. However, at the value B, this is just a vertical line, and a line is one-dimensional. Area is two-dimensional. So there is no area here. So the answer here would be 0, because there is no area. No area when our variable equals a particular value. And remember, we're in the continuous world. So these two first examples with the pink and green zones, those encompassed areas, and so you definitely could get a value for that. This brings up an important distinction with continuous random variables. Continuous random variables, in order for us to consider probability, we need to be able to obtain some calculation for the area. And the only way that's going to happen is to consider the variable over an interval, right? Like A to B, less than A. So that way we can get that area region. So the probability that a continuous random variable equals a specific number is 0. This brings up another point, that in a continuous world, the probability, I need some spice, the probability that, say, your variable is less than A, okay, so that's going to be over an interval, and the probability that your variable is less than or equal to A, the only difference here is this less than or equal to portion. And this would include the one additional point of A. On the left here, this is less than A, so it does not include A, this includes A. But the probability of exactly A is 0. So therefore, these two statements say the same thing. So notice the inclusion of that one extra point, less than versus less than or equal to, really does nothing to those probabilities. In a continuous world, the same is true if you use greater than and greater than or equal. And I'll write down the reason, because the inclusion of A adds no additional probability. That's going to conclude this video. We will discuss continuous variables a lot in the future, so keeping this brief here. And in the next video, we will introduce cumulative distribution functions.